Hello, this is the ninth module of the course on econometric modeling. So, till the previous module we have introduced the methodology under simple regression, and I have also discussed the assumptions behind OLS. Now, this module basically talks about the properties of the OLS estimators. OLS estimators needs to have certain properties which are primarily dependent on the assumptions that we make. These properties are essential for the OLS estimators because until the assumptions are not fulfilled, the properties will also not be met, and accordingly the application of OLS on certain problem might not be relevant or the right one. So, from that perspective, OLS properties or the properties of OLS estimators are important things to discuss. First of all, I just mentioned that if the assumptions of CLRM holds, then OLS estimators are known as best linear unbiased estimators. So, this actually summarizes the properties or the most important characteristics of OLS estimators. Best here means that the OLS estimator beta hat as well as alpha hat has minimum variance among the class of linear unbiased estimators. Linear means alpha hat and beta hat are estimators of a linear relationship between x and y. The concept of linearity has already been discussed at length, and again here it implies that only linear relationships can be estimable using or can be estimated using OLS. So, alpha hat and beta hat are linear estimators of the relationship between x and y. They are unbiased. This implies that on average the actual values of alpha hat and beta hat will be equal to their true values. So, first we talk about the unbiasedness. I said it is represented by blue. So, best linear unbiased estimators, alpha hat and beta hat are estimators. We begin with first of all unbiasedness. Linearity has already been discussed. So, at the end or next we will be discussing best, and there is another property which is the property of consistency that will be discussed after that. So, the OLS estimates of alpha hat and beta hat are unbiased if expected value of alpha hat equals alpha and expected value of beta hat equals beta. This essentially implies that in repeated samples from the population, if we obtain alpha hat and beta hat, then their expected values will be equal to the population parameters. Thus, on average the estimated values of the coefficients will be equal to their true values. That is, there is no systematic overestimation or underestimation of the true coefficients. So, the true coefficients may vary slightly from the actual parameters, that is alpha and beta, but the thing is that there is no systematic overestimation or underestimation. So, whatever little overestimation or underestimation could there be, that is completely random. The assumption of zero covariance between x and u or expected value of u given x equals to 0 is crucial for unbiasedness of alpha hat and beta hat. We will be proving the unbiasedness of alpha hat and beta hat. So, first of all we consider beta hat. So, remember from module 6 that we obtained beta hat, that was the formula for beta hat that we had obtained, or this can also be written as summation x t minus x bar multiplied by y t divided by summation x t minus x bar whole square. That is because x t minus x bar multiplied by y bar is 0. So, if I expand this expression, that is summation x t minus x bar into y t minus y bar, then I am retaining only this part and claiming that summation x t minus x bar multiplied by y bar is actually equal to 0. That is because y bar being constant, it actually comes out. So, this is equivalent to y bar multiplied by summation x t minus x bar equals to 0. Now, this can be written as further Now, focusing on only this part, you can see that if I write n into summation x t by n minus summation x bar, this is equal to the first part I am multiplying by n and dividing by n. Now, this part is x bar. So, I have n x bar minus, when I sum this x bar, which is a constant number n number of times or capital T number of times. So, here I am using here I am actually summing over I equals to 1 to n. I could have summed over T equals 1 to capital T, but then summing over from I equals 1 to n, I have n x bar, this is equal to 0. So, that is why we have this part equals to 0 and beta hat is simply summation x t minus x bar multiplied by y t divided by summation x t minus x bar square. In terms of population coefficients and error terms, beta hat can be written as this, where I am simply expanding the value of y t or the expression of y t. So, y t, as you know, originally is alpha hat alpha plus beta x t plus u t. So, simply this expression is replaced here in place of y t. Now, when I am focusing only on the numerator, so expanding the numerator, I have alpha into summation x t minus x bar plus beta into summation x t minus x bar multiplied by x t and then plus summation x t minus x bar, this thing multiplied by u t is the last expression. We have already proved that summation x t minus x bar is equal to 0, right. So, alpha hat into summation x t minus x bar is actually equal to 0. So, I am left with the rest of the thing in the numerator, denominator usual I have summation x t minus x bar whole square. Now, it can be shown that summation x t minus x bar into x t is actually equal to summation x t minus x bar square. That is actually that can follow from here itself, that this expression can be written as summation x t minus x bar into summation x t minus x bar, right. The square is just broken, and if I further write it as summation x t minus x bar into x t minus summation x t minus x bar into x bar, then x bar comes out because it is a constant term and this term is equal to 0. So, I am simply left with summation x t minus x bar into x t. Now, if you remember, or rather let me show you that we had this expression for beta, where we have beta multiplied by summation x t minus x bar into x t. I just showed that this expression is equivalent to this expression. So, if I separate these two entities, then what happens is that we have beta multiplied by summation x t minus x bar whole square in the numerator and also summation x t minus x bar whole square in the denominator. So, they cancel out and I am left with simply beta, and then we have plus summation x t minus x bar u t divided by summation x t minus x bar whole square, the usual second part. Under the assumption that the expected value of each u t conditional on x 1, x 2 to x n is 0, this part will be 0 when we consider an expected value ahead of it. So, since this is conditional upon the x values, so all these summation x t minus x bar whole square and summation x t minus x bar, all of them becomes non-random, and consequently we have summation expected value of summation u t, and that is actually equal to summation, as well as along with the fact that we have covariance between u t and x t, these two assumptions taken together renders this expression 0. Hence, we have expected value of beta hat equals to beta only. Since unbiasedness holds for any outcome on x 1, x 2 to x n, unbiasedness also holds without conditioning on x 1, x 2 to x n. So, for any outcome on x 1, x 2 to x n implies that for any functional forms of x's, the unbiasedness holds, as a result of which we can say that it also holds without conditioning on any values of x. Now, talking about the unbiasedness of alpha hat. Alpha hat as we already know is y bar minus beta hat x bar. So, what we are doing is that simply replacing the values of y bar with alpha plus beta x bar plus u bar. We know that u bar, expected value of u bar will be 0, and we have alpha plus beta hat minus beta minus beta hat x bar. So, taking expected value, we have alpha plus since alpha is constant, we do not take expected value of alpha. Expected value of beta minus beta hat x bar plus expected value of u bar is equal to alpha, because expected value of u bar is 0 and this expression is actually this, and we know that expected value of beta is beta and expected value of beta hat will also be beta if beta hat as an estimator is unbiased, and as a result of which we have also this expression becoming 0, expected value of alpha hat is alpha. So, that is how we prove the unbiasedness of alpha hat and beta hat. Now, we talk about efficiency. So, best implies minimum variance estimators, and this is actually an alternative term for best estimator is the most efficient estimators, or alternatively we call the assumption of efficiency. Any set of regression estimates alpha hat and beta hat are specific to the sample used in their estimation. As I am saying that as the sample changes, alpha hat, beta hat, or estimates of alpha hat and beta hat changes. In other words, if a different sample of data was selected from within the population, the data points, that is xt and yt, will be different, leading to different values of the OLS estimates, that is alpha hat and beta hat. An estimator beta hat of a parameter beta is said to be efficient if no other estimator has a smaller variance. Broadly speaking, if the estimator is efficient, it will be minimizing the probability that it is a long way off from the true value of beta. So, lower the variance, lower is basically on average the deviations beta as an estimator or beta hat as an estimator will take from the population parameter beta. So, lesser the variations, the better the estimate is, and that is why this is a desirable property, the property of efficiency, that is alpha hat and beta hat both are supposed to be the minimum variance estimators. It is thus useful to know whether one can have confidence in the estimates and whether they are likely to vary much from one sample to another sample within the given population. So, lower the variations, sample to sample estimates will be also less different. An idea of the sampling variability and hence of the precision of the estimates can be calculated using only the sample of data available. This estimate is given by the sampling variances of the OLS estimators conditional on the sample values x1 to xt. So, now we talk about sampling variances, and we also basically derive sampling variances or the sampling variances of the estimators. Now, remember this was the expression of beta hat, right. Beta hat, we arrived at this expression. After that, taking expected value of beta hat, we proved that expected value of beta hat is equal to beta, which implied unbiasedness. Now, we begin from this expression. Note that beta is just a constant and conditional upon x. So, which renders summation xt minus x bar whole square and xt minus x bar. So, this component and this entire component both also are non-random. Also, because the ut are independent random variables across T, which is the assumption 3 or under CLRM, that is classical linear regression model, the assumptions that we made in the previous module. The variance of the sum is the sum of the variances, and which implies that if all of them are independent, then there will be no covariance between the terms of which variances are considered, and as a result of which what we obtain is this is the variance of beta. So, how do we arrive at the variance of beta? If you remember, I discussed that variance of x is basically expected value of x's square, right. Now, which is sum of individual observations subtracted minus the mean of the variable. Now, this implies that the moment I take a variable out of the variance expression, I need to square it. So, this being non-random is taken out of the variance operator and it has been squared. So, in the denominator, or first of all we have 1 minus summation x t minus x bar whole square, the entire thing whole square, and we are left with the variance of the numerator expression summation x t minus x bar minus u t, summation x t minus x bar multiplied by u t. Okay. This is also non-random. So, this also come out with a square term and I am left with variance of u t only. We already have discussed the variance of the population error term and that was denoted by sigma square. It can also be alternatively denoted by sigma square u. So, currently going with the expression of sigma square, we have sigma square here and that is how sigma square. Now, you note that sigma square being constant actually come out of this summation operator. So, when it comes out of the summation operator, I have sigma square multiplied by summation x t minus x bar whole square divided by summation x t minus x bar whole square, the entire thing whole square. So, this shows that this thing actually cancels out and that is how we have only summation x t minus x bar whole square in the denominator and sigma square in the numerator, that is the variance of beta or rather beta hat. Similarly, the variance of alpha hat can be obtained as this. Now, variance of alpha hat, the derivation is slightly longer. So, I am not getting into the derivation, all these are available in the standard textbooks I have referred to. Beside that, the derivation of this will be easier when we get into multiple regression and then in the matrix form we can actually reduce the variance of alpha hat and beta hat, or rather the variance of the constant term more easily. So, this is the variance of alpha hat where sigma square again is equals to expected value of u square, that is variance of u, and both variances are conditional on the sample values of x 1 to x t. So, that was about efficiency or minimum variance estimators. I had just derived the variances of the estimators. There are proofs which shows that in the class of estimators, OLS estimators are basically the minimum variance. I did not get into the proof of those the minimum variance estimators of that alpha hat and beta hat are the minimum variance estimators. Next we talk about the property which is consistency. This is basically a large sample or asymptotic property. So, as the sample size increases, now probably we observe this property among the OLS estimators. So, the least square estimators alpha hat and beta hat are consistent when probability limit t tends to infinity, alpha hat minus alpha the mod value is greater than delta is equal to 0, and similarly we have an expression for beta. So, this is how we define consistency. Now, what does it imply? This is a technical way of stating that the probability that alpha hat or beta hat is more than some arbitrary fixed distance delta away from its true value tends to 0 as the sample size tends to infinity for all positive values of delta. Alternatively, in the limit, that is for an infinite number of observations, that is as my sample size grows, the probability of the estimator being different from the true value is actually 0. So, simply putting, as my sample size grows to infinity, that is the sample approaches the population, the probability that the estimated alpha hat or estimated beta hat will differ from the population alpha and population beta by any positive number is actually 0. right. So, this is the property of consistency, which is actually, as you can see, a large sample or asymptotic property. Now, we briefly just talk about the algebraic properties of OLS statistics, that is, first of all the sum, and therefore, the sample average of the OLS residuals is 0. So, we have assumed that the population error, the expected value of population error is 0. Its counterpart sample residuals tend to have an average which is equal to 0. So, summation t equals 1 to t or summation n equals 1 to I equals 1 to n ut or ui is equals to 0. Alternatively, this can be written for summation I equals 1 to n ui is equals to 0. This is for cross section and this is for time series. Otherwise, there is as such no difference. This follows immediately from the OLS first order condition. If you remember, the OLS first order condition was summation yi minus alpha minus beta xi equals 0, I running from 1 to n, or we can replace it with t. This is actually is equivalent to ui. So, that is why it directly follows from OLS first order condition. The sample covariance between the regressor and the OLS residuals is 0. So, we assumed it for the population counterpart, which is one important assumption of the CLRM, and for the sample we are considering it to be one of the algebraic properties of the OLS statistics, and this is actually not an assumption. This ideally the sample counterpart of the population assumption, that is the covariance between the regressor and the OLS residuals is 0. So, summation t equals 1 to capital T x t u t equals 0. Alternatively, I can write summation I equals 1 to n x I u I equals 0. These two properties follow immediately from the OLS first order condition. So, this also follows from the OLS first order condition. This is actually obtained when I divide or when I take the first derivative of the residual sum of square with respect to alpha hat. This follows when we take the first derivative of the residual sum of square with respect to beta hat. So, if you remember, this is actually equal to xi into yi minus alpha minus beta xi equals to 0, I running from 1 to n. So, these two properties follow from the OLS first order condition. And the final algebraic property is that the point x bar y bar is always on the OLS regression line. This has also a very simple proof. If you remember, yi is actually equal to alpha plus beta alpha hat plus beta hat xi plus I have the error terms, that is or the residual. So, ui hat. Now, if I take the average, so I have summation yi equals, here we have summation alpha hat, which is n alpha hat, plus summation beta hat xi, which is beta hat summation xi, plus summation ui hat, that is the residuals. Now, when I divide both the sides by n, then you can see I can write it as y bar equals alpha hat plus beta hat x bar, and this is equals to 0, straight away follows from here, right. So, plus 0. So, this shows that when x is at its average for given values of alpha hat and beta hat, y will also be at its average. So, alpha hat and beta hat basically for any values of the slope and the constant term, when x is at its average, y hat will also be at its average, and since this expression is true, that is why we can say that the regression line always passes through the averages of both the variables, right. So, this actually brings me to the end of the discussion on properties of OLS estimators. These are the books that I have followed for, or you can follow for the discussion on the properties of OLS estimators. Thank you.